Let's explore gas pressure. Here we have 4 different types of refrigerant. This is a digital gauge, 0 psi. This is a thermistor. This will measure the temperature. About 59 degrees out here right now. These jugs have been in my van all day. So I'm going to see what the temperature of the jug is. It's still dropping a little bit. But thanks to the ideal gas laws and us knowing what gas is in each of these jugs, we can actually take that temperature, take a pressure temperature chart for this exact refrigerant, and based on the temperature, we know exactly what the pressure will be. So as I open this, that gauge will read the pressure inside this tank. Currently we're at 62 degrees. This is 410A refrigerant. So we find 410A. Our temperature is currently 62.1, so should land somewhere around 176 psi. That'll be our pressure. So as we open this, so we're about 1.5 degrees off. I ain't worried about that. I'm measuring the temperature on the exterior of the jug. That's not necessarily what the internal temperature is of the liquid refrigerant at the bottom. And for just 1.5 degrees, the gauge may just need calibrated. But we can do that for each of these. So for 417C, we're going to land 73 degrees or a little above that. 417C. $76.8. Again, I'm just basing these on the temperature of the first jug. So somewhere around 61 degrees. 404A, around 62, somewhere in the ballpark. 128 PSI, 128.6. And our actual 128.4, that one's spot on. We got 134A, this is what goes in your car. So 134A, around 62 PSI. And with it, we have 57.1. Alright, here's what we should expect to see if we were inside of a container with a fixed amount of gas and the temperature changes. We have our 404A refrigerant. It's at 60 degrees, 127 PSI. We have some ice water here. So as we put this down into the ice water, we can see the temperature is going down. We can also see the pressure is going down. There's no gas leaving this jug. The temperature is changing, therefore the pressure is changing, which is exactly how refrigeration and HVAC work. We just use a compressor to manipulate that pressure, which will force the temperature to change. So you change either one and the other will have to change. We just exploit those properties. So we removed it from the ice water. The temperature is starting to go back up, pressure is starting to go back up. And any HVAC tech will tell you in the wintertime we do the opposite with hot water. It's so cold outside our tanks don't have enough pressure, so we'll get a bucket of hot water, put the tank in the hot water, increase the pressure, charge the system. So we had about a 35 psi drop with like a 20 degree temperature drop. And if we would have left the jug in there, it would have continued the drop. 404A getting down to 32 degrees would have went down to 72 psi. So that's why it just does not make sense that we have an actual dome over us. A firmament, yes, our atmosphere is a firmament. It protects us from asteroids and meteors coming in, helps break them up, protects us from the solar radiation. So yes, we can still have a firmament without having an actual container to hold pressure in, because our pressure is not from the quantity of gas that is squeezed into a fixed volume. The pressure here at ground level just does not fluctuate enough for the temperature changes that we observe. It can go from 110 degrees down to -15, colder and hotter in some areas. Yet we still have around that 14.4, 14.8 psi, or somewhere very close to that. Space is not a vacuum that sucks everything out. It's called a vacuum because it's just void of material. The same thing that makes this fall downward is what holds the gas molecules to the earth. Once you get above 200,000 feet, there is no gas pressure. There is gas, but there's no pressure. There's no weight. So that's why you don't have pressure against a vacuum. Just doesn't exist. I'll do one more video here on gas pressure a little bit later, try to wrap it up, and we'll just use normal air around us. So all the gas laws out there are talking about a fixed volume, a fixed temperature, a fixed pressure, or how changes to one will affect the other. Any one of the triangle. None of that applies to atmospheric pressure. None of it's observable in atmospheric pressure. So please stop trying to use that as a reason that you can't have pressure without a container. When you do have pressure in a container, it exerts the pressure equally at every point inside the container. It would not be a gradient. We only see the gradient here in the atmosphere because it is from the weight of the air above it. The higher you go, the less weight there is above you, so the less pressure is exerted on you. It really is no different than going deeper into the water. So hopefully you guys learned something new, or at least was entertained. Have a good one.